Okay, welcome everyone. Before the session starts, I'd like to say a few words. First, I want to thank everyone here today attending the session, and hopefully by the end of the session, you'll find that your time is worth it here. And second, I want to give appreciation to Charlie for spending a significant amount of time preparing the slides and the great contents he will be giving us momentarily. So, without further ado, let's just get started the session. Welcome, Charlie.
Good afternoon, everyone. First, I would like to give you all a thank you so I don't have to embarrass myself lecturing into an empty hall. Thank you, really appreciate that. Let me just give a few words to introduce myself. My name is Charlie Liu. I'm a sophomore at Brown College, currently double majoring in operations research and computer science. I've been practicing for competitive programming, CP for short, for about 4 years, 2 years. I started in high school, about 2 years in high school and 2 years in college. I'm currently on Rice's ICPC team, Rice Alps, and last year our team competed our way all the way to the North American Championship, which is something we are kind of taking pride of ourselves. So today, the title of our slide is Pre-SCUSA Educational Session. Oh, sorry. Let me see. Does this work?
Yes.
Okay. So as you can read from the title, the topic today is Pre-SCUSA Educational Session. Just see a quick raise of hand. Who is going to participate in SCUSA? Anyone? No one? Okay. So if you're watching the recording and you're going to participate in SCUSA, which is coming up in 4 days, this slide will contain very important information that will help you to perform your best during the competition, because it's going to contain a lot of useful tricks, hacks, tips for programming competition. And if you are not going to participate in SCUSA, but in general you just want to become a better competitive programmer, or even more generally you want to become a better problem solver, I will contain many knowledge in this slide that will help you to become a better problem solver or a competitive programmer in the long run. What I will not talk about today, however, is I'm not going to talk about what is CP and we should do it, because this is not a club fair for our ICPC club. It is not like intro to CP presentation. If you're here today, or if you're watching this recording right now, I assume that you are at least somehow interested in become a better competitive programmer, or in general just a problem solver. I will also not talk about specific algorithms or concepts, because we don't have nearly enough time today to do any algorithms justice. That should be your sort of homework that you should do when you are on your own. But what I will talk about today is what are the algorithm concepts that are most useful in competitive programming context. So it will provide a sort of a roadmap. So when you figure out your journey through the world of competitive programming, you know where you should go next. So without further ado, let's begin. This lecture is roughly divided into 7 sections. The first section was called the basics, which gives a brief overview of the tips and tricks and contest mentality that I think is going to be very useful. In CP, I'm also going to talk about problem solving strategy. Whenever you see a problem, and you're like, I have absolutely no idea about how to approach this problem. So in the problem solving strategy section, I will talk about what are some steps you should take to figure out how to approach a problem. In the third section, it's called the book section. The book in CP community refers to reference material that you can bring into a competition that will help you to code up standard routines really fast. Next section, I will talk about in-contest strategy. How do you manage your time? How do you prioritize the problems? and how do you approach the problems in general. In the next section, I will talk about the common mistakes that beginners tend to make and how to avoid them, because I think that will be of tremendous value for those who are going to participate in the forthcoming school staff, or in whatever programming competition you're into. Next section, I will talk about teamwork. If you don't already know, SchoolSat is a team competition. You compete in teams of 3. So how do you work with each other to maximize your ranking? That is actually quite in depth, and it has a lot of structure into it. And for the last section, I will talk about how do you improve. It's sort of like a meta section that teaches you how to improve in the long run, how to become a better competitive programmer, how to become a better program solver in the long run. So without further ado, let's start with the basics. So in competitive programming, there is, let me actually move this Zoom thing around so it does not block the screen. In CP, what is the only thing we care about? One word. Anyone?
Solutions. Speed.
Yes, exactly. It's speed. And the speed comes from 2 aspects. It's the speed at which you can type out your solution, and the speed at which your solution runs. Now, with that in mind, the first question you want to ask yourself is what language you want to use. And the answer is almost always, with some caveats, C++. Why? Because C++ is pretty much the fastest language out there. Compared to Java, it is 3 times faster, and compared with Python, it is about 20 times faster. So C++ is definitely your go-to language. I know it's a bit hard to learn, but if you're doing CP and you're sort of committed to it, it's definitely worth learning. And just even outside the CP competitive programming context, C++ is of extreme value in long term in your career, whatever you want to do. Have you ever guys read posts that saying C++ is dying language? Anyone? It's not. Okay, you're gonna die. I'm gonna die. C++ is not. It's gonna live, right? So it's definitely worth spending some time learning C++. And the thing about the algorithmic context is the most. Let me put it this way: you really want to get the complexity of your algorithm right. If you get the complexity of your algorithm right, then there will be some tolerance of what is the constant factor your algorithm run at. So for example, if you code up your algorithm which has the right complexity in the fastest way, even if your program somehow runs 50 times slower, the time limit will still allow you to pass it. But still, you want some freedom to do whatever thing you want. So my suggestion is use C++ as your go-to language, because it will allow you the most amount of freedom in what constant factor you have in your algorithm. There are some exceptions to this rule, because there are certain things that are much easier done in Java or Python than C++. For example, when you are dealing with really big integers, for example, the one that overflows a long that is greater than 2 to the 63, there is no a standard library in C++ that allows you to handle big integers. So when you have to deal with that although it does not happen very often, but when it does, you can use Python, because in Python you don't get integer overflow. And whenever you want to do some fancy operations that involve list operations, Python have a very flexible list operations that you can use in your armory. So consider that. And whenever you deem necessary, right? There is no a set of rule that you have to follow. You can always be flexible, but whenever you choose to use a slower language, Java or Python, just keep in mind that Java is about 3 times slower than C++. Python is about 20 times slower than C++. Keep that in mind and be careful when you're writing it. So, since we brought up C++, I think it's helpful to talk about what part of C++ is most useful, because when you want to master competitive programming, you don't really have to know the entirety of C++, right? Like besides like a few people on this planet, like I don't think anyone really like knows the entire everything of C++. We're going to use a subset of C++ in our competitive programming. And as you can see on the slide, it's really a very limited subset of C++ that you're going to use. So the common containers we use in C++, vectors, which you can basically treat as a Java array list or Python list. Very handy. It's the, I'd say, the container that I use the most. Queue, when you want a FIFO structure, first in, first out, you want to use a C++ queue. Here's a quick question for you. I have queue here, but not stack. Do you guys know why? Because the stack and queue usually come together, right? Why do I list stack, but why do I list queue but not stack? Anyone have any idea?
You can construct a stack with a queue.
That is correct. That is very hard. The correct answer is you can basically use vector as your stack, because C++ vector it has two memory functions. It has pushback and popback. When you only access the vector using these two methods, your vector is effectively a stack. So when you can do things with a vector, when you stack, right? That's my personal choice. You can use stack if you want, but just keep in mind, like just using vector as a stack is always an option. Pair, extremely useful when you're considering, well, pair of objects. It's mostly commonly used to represent, for example, coordinates in XY plane, where the first entry is the X coordinate, the second entry is the Y coordinate. Very useful, very handy, and it has a natural order, a dictionary order that comes with it. Tuple is just a pair, but with more entry to it. When you want to use sort of quote-unquote pair with 3 or more entries to it, you can use tuple. Bset is basically a Boolean vector, but it is much faster and much more memory efficient than a Boolean vector. So whenever you want to create a gigantic Boolean vector, use Bset. It will make your code run much faster and use much less memory. Set is basically what it sounds like, a set. It can contain non-repeating elements and check whether an element is in set, delete from the set, insert into a stack with time log n. And map is very similar to set, except it not only stores the element, it stores the key value pair. So you can, for example, use string as a key and integer as your value. So when you ever throw in a string, you get an integer that returns you, for example, the ID of the string, something like that. Priority queue, extremely useful. It's a data structure that stores the thing that has a natural order on it. For example, integers. You put a bunch of integers into the priority queue, and you pull from the queue. You always pull the largest integer from your set. And a couple of useful C++ function. Find, which find if an element is in data structure, and sort, which does exactly what it sounds like. It sorts the element in a data structure. And for initializers, I have memset, which you can use to fill an array with either 0 or -1. Do not attempt to use memset on any other value than 0 or -1. It doesn't work. We want to fill an array, for example, with 2 or 1. Use fill, because it's basically memset slower but more versatile, because you can fill the data structure with other values other than 0 or -1. By the way, do you guys have any idea why 0 and -1 are so special? When written in binary, what is 0?
Sorry, I was actually ask a question.
Yes.
So I missed the part that you said, like, when you're trying to use 0 and -1, which one can you use?
Both. Okay, map set can be used to fill an array with 0 or -1. Like you can choose what to map set.
And what about the field?
Sorry?
What about the other one, the field?
You can use field to fill anything, any number or any.
It's because the Boolean value of 0 and -1 are false.
Can you say that again?
Boolean value of 0 and -1 are false.
Okay, so I think you're getting close. The answer is when writing out in binary, this is 0. The binary representation of 0 is just 0, 0, 0, 0. And the Boolean representation for -1 is 1, 1, 1, 1, 1. So when you just flash a stream of 0 or -1 into a data structure, it will always get you an array of 0 and -1. It does not necessarily work in the same way for other numbers, right? The Y method works only for 0 and 1 is because 0 and -1 is just all 0 or all 1. Okay. Continue on our topic on C++, here are some small hacks that are generally considered a best practice in computer science or in an industry, but are quite useful in competitive programming. So here are some of the tricks. So definitely use tabdef. Tabdef basically allows you to customize your the type name to something else. For example, when you are going to use a bunch of long, just typing out long everywhere is going to be very time consuming. As we said before, in CP, the only thing we care about speed, and one aspect of speed comes from the speed at which you can type your code. So when you type that long LL, whenever you want to type long, you can just type LL, which will save you a lot of time. Like a lot of practitioner of competitive does that. And also pair int, very common to represent integer lattice in XY plane, PII, vector of int, BI. That will make your life much easier when you want to define variable of these types very frequently. Another quick and dirty trick is the first line of your C++ file should always be include bits std c++.h and using namespace std. Don't do that in your whatever CX class you're doing. Like if you do that, like your professor is going to probably blast you. But this bits std c++.h, it basically contains everything you're ever going to need. So instead of using the only import what you need principle and include math, include algorithm, include CMath, include IOStream, that's just a bunch of include that you're going to spend a lot of time typing. You're just going to include bits std c++.h. It takes 2 seconds to type it out, and you include everything you're ever going to need. So use this, and using a namespace std, it just allows you to type cout instead of std : cout, which saves you some typing, saves you some time, which increases your speed, something that we think is desirable. And always pre-allocate the file size. Again, widely considered a bad practice by the computer science community, however, extremely useful in programming competition, because instead of using dpn, where you read n from the problem, you just allocate the full size on the at the beginning, so you don't have to worry about adjust the size later. If you are worried about overflowing long, which rarely happens, but can sometimes happen, there is a variable type called underscore int 128, which is a 128 bits integer that can store much bigger numbers than long. That's pretty much the limit of C++. You can have a 128 bits integer. If you're going to use more than that, use Python. And fast I/O. At the beginning of your main function, just throw draw these two lines, it will automatically make your input go 5 times faster. How? Like magic. Okay, just it comes for free. Like you often hear people say there's no free lunch. There is, that is. And don't worry about style. Don't worry about comment. I know like that two things get emphasized a lot in your computer science courses. Here's my question for you. Does style help your code to run faster? No. Does comment help your code run faster? No. Does it help you write your code faster? It does the opposite. Forget it. Throw it out of the window. We don't care about them in competitive programming. The only thing we care about, just to reiterate, is speed. The speed at which your program runs, the speed at which you type up your code. So now we are over with C++. Let's talk about algorithm complexity. So if you've ever done like a single problem in CP style, you'll probably recognize that in the input section, they will specifically say what is the limit of their data. And that is very useful information for you to judge, okay, what is the worst algorithm that I can write to make sure my code passes the time limit. So typically in a CP problem, the time they allocate you goes from 1 second to 10 seconds. So it's just like a few seconds. And a rule of thumb is for 1 second, you can pretty much allow the order of 10 to the 8th operations for 1 second. Now, what does that mean? When you see n is less or equal to 10, you can afford a factorial algorithm that can pass the time limit with ease. When you see n less or equal to 16, you can probably afford n times 2 to the n or n squared times 2 to the n. That's typically the time complexity of a bit mask DP. When you see n less or equal to 20, you can afford something 2 to the n. N less or equal to 100, exponential algorithm does not work because 2 to the 100 is just enormous. You have to write something polynomial. It's either n cubed, or if you can write a really fast n to the 4th, you can probably do that. When you see n is less or equal to 1,000, n squared, you can pass that easily. N squared log n, no problem. When you see n less or equal to 10 to the 4, which I personally don't find to be very frequent as the size limit in CP, but for n less or equal to 10 to the 4th, a very fast n squared will probably pass. For n less or equal to 10 to the 5, it's most likely to be n log n. But a fast n squared n will also pass. And there are some occasions where you are going to write n times log square n. That is also okay. When you see n less or equal to 10 to the 6, you really want to aim for a linear time algorithm. Or if you can do a really, really fast n log n, you can do that, but that's like sorting. Yeah. And so far in my CP career, I have never seen a problem with input data size that is greater than 10 to the 6. Anyone have an idea why they don't have that?
Anything's faster.
Because if you only have return statement and return 0, is that gonna like, I don't know. Which means that like basically the input, like if you process each input like in one, probably, I mean if you even if you process each input once, that's still not enough time.
Yes, correct. The correct answer is if you have some data that's 10 to the 7, just read the input into your program. It's probably going to take a few seconds and exceed the time limit. There is just no point for them to give you a data set of such large size. It just doesn't make sense. So these are like 10 to 6 is like the most large data set you're ever going to encounter in a programming context setting. Here are two memes. The size on the size limit on the data isn't just telling you what's the worst algorithm you can have. It is often a hint for what is the intended, quote unquote, intended complexity for the solution. For example, when we see n less or equal to 16, to an untrained eye, that's just n less or equal to 16. But for a seasoned competitive programmer, it screams like something exponential, right? Because if the problem is polynomial solvable, they'll probably give you a much larger data set. The only reason why they're going to have such a small n is they have something exponential in their mind. So n to less or equal to 16, do you guys remember what is that again? What's the worst time complexity?
To the power of n.
Yeah, to the power of n times n or n squared, right? So that's typically the time complexity of a bit mask dp. So when you see n less or equal to 16, think about, can I somehow apply bit mask dp to this problem? Here is a more classical name that's more widely spread in the CP community. When you see n less or equal to 100, think about flow, the max flow model, which I will talk about later. Here are some good numbers you should keep in mind. 2 to the 10 is 124. You should probably know that, which is approximately 10 cubed. 2 to the 20 is approximately 10 to the 6. The largest value you can store in an integer is 2 to the 31 minus 1, which is approximately 2 times 10 to the 9. That gives you an idea, okay, when should I just keep using int, and when do I have a possibility of overflow an integer, so I probably should switch to long. The maximum number you can store in a long, 2 to the 36 minus 1, which is approximately 9 times 10 to the 18. That gives you an idea like when you might flow a long and maybe considering using int 128. 10 factorial is about 3 times 6 times 10 to the 6. So when you decide to write a factorial algorithm, it gives you an idea about how much time you have left to do something on each of the permutation of the whatever elements you have in hand. The square root of 10 to the 5 is approximately 320. If you're thinking about doing a square root bracketing on a data set with 10 to the 5, that should be the size of your bucket. Finally, does anyone know what the pi means in this context? What is the pi function?
I remember I learned it the. Sorry, I'm actually not sure.
Okay. It's actually the prime function. So pi of x counts how many prime numbers are there less or equal to x. So there are 9,592 primes less or equal to 10 to the 5, which is approximately 10 to the 4. There are about 80,000 prime numbers less or equal to 10 to the 6. So when you're doing a number theory related problem, these are two quick numbers you should have in your mind to let you judge, okay, like how many prime numbers I need to keep track of to solve certain problems. Now, in your computer science course, you talk about like how to do time complexity analysis, right? And like a large family of algorithms can all have complexity of, for example, O n to the square. But constant in competitive programming does not matter as much as complexity, but it certainly still matters. So there is a difference between different O of n squared, and O of 1. So here are some common operators you use in competitive programming, plus or minus, which are really fast, and bitwise operations, bitwise AND, bitwise OR, bitwise XOR, left shift, right shift are just as fast, if not faster, than plus or minus. So these are really fast O of 1. Multiplication and division tends to lie on the slow side of the spectrum. And the modular operator, the percentage sign, is a really slow operator. So when you're doing a counting problem, for example, and you're modding your answer with a very large prime number, try not to spam that modular operator and only use it when absolutely have to, aka when you are about to get overflow, when you perform a certain operation. And here is a quiz for you. When you are doing a modulo 10 to the 9 plus 7 problem, should you use int or long null? Why? Okay, what's the largest number int can hold? 2 times 10 to the 9. And 10 to the 9 plus 7 is less than that. Why do we still want to use long null?
Oh yeah, I thought this was bigger than that.
Sorry?
I counted the zeros wrong.
Oh yeah, there are 9 zeros. Oh sorry, 8 zeros and 7.
Yeah, I counted.
10 to the 9 plus 7.
I counted the zeros wrong.
But do you want to change your answer?
Yeah, and I think int would work.
You should still use long null. Why? Although all of your answers are going to be less than 10 to the 9 plus 7, in the process of your computation, for example, when you want to multiply two things together, this will definitely overflow int, but it will not overflow a long null. Because remember, what's approximately the largest number a long null can hold? Yes, 10 to the 9 times 10 to the 18. Right, that's only 10 to the 9, so we square the number, you got 1 times 10 to the 18, which is definitely less than 9 times 10 to the 18. And here are what I call two useful bitwise operation tricks. Yes?
I want to tell things that if there are only 7 zeros, it's still a prime. I mean, 1, 7, 0, and 7 is still a prime.
Oh, okay.
Some problem description use this prime instead of this classic prime.
Yes. Okay. So Regine brought out a really interesting point. When you that is a topic for a more experienced competitive programmer. Like because the prime 10 to the 9 plus 7 is so famous, when you see 1, 0, 0, 0, a bunch of 0, and 7, you might just assume it's 10 to the 9 plus 7. But sometimes it might not. Like I have personally seen a problem where there is 10 to the 8 plus 7, and like in the comment section of that problem, like people were like mad, right? So my advice for you is be careful, like counting the zeros, or another way, just simply copy the number from your program and paste it in your program. Back to the slide. So two quick tricks about a bitwise operation. When you want to judge if x is an even or odd number, instead of doing the modulo 2 operation, you can simply bitwise AND it with 1, and it will return the exactly same answer with modulo 2. We want to divide something by 2, of course, an integer by 2. Instead of doing just the normal division, you can just bit shift it left by 1 digit, and it will return exactly the same answer as divided by 2. Similarly, not all log n's are created equal. The log n that comes from sort, infinite tree operation, binary search, priority queue, this tends to be the fast log n or log n out there. Set tree are okay, they're still rather fast. The log n from set, map, display, linked tree, the later two I will talk about later, are really slow. So whenever, I'm not trying to say like avoid them when possible. You just have it in your mind that these are on the slower side of log n. Here is my quick question for you. If you want to check if a number x is in a set, should you use the first approach or second approach? Anyone? Volunteers? Okay, let's yes, Peter.
You mean like should we use the Boolean one or just that? Or is that what you mean by first and second approach?
say there's a subtask in your program. You want to check if number x is in a set.
Okay. Okay, I think the second approach, the vector Boolean model, would be faster.
You're 50% right.
Okay.
Because the correct answer is it depends.
Um,
It depends on the range of x. If x can be as large as 10 to the 9, guess what? Just creating a Boolean vector or even a bit set of length 10 to the 9 will probably lead you to a memory limit exceed or TLE, right? But if the range of x is only something like 10 to the 5, definitely use the second approach. So the correct answer is if x is really sparse, right? There are only a few x, but it spreads over a very large range, use the first approach. But if x are quote unquote like dense, like there are approximately the same number of x's as like the range of x, use the second approach. The first approach will give you O of log n per query, and the second one will just give you a O1 per query. So something you should have in mind. So now we're done with basic. We're going to move to a problem-solving strategy. So what do I mean by problem-solving strategy? When you see a problem and you read the description and you're like, Jesus, I have no idea how to approach this problem. Okay, what are the steps you can take? The first question you should ask yourself is the problem brute forceable? Is the input small enough, or is the time limit lenient enough for you to somehow search all possible solutions? Something to always keep in your mind is you're not trying to find the best solution. The solution has the fastest time complexity. You're trying to find a solution that passes the time limit while producing the correct answer. For example, if you have an input that's n less or equal to 1,000 and you have 1 second as your time limit, you can spend half an hour trying to come up with a log n algorithm. But that's just stupid. You don't get extra credit for coming up with an extra fast algorithm. If you can find an n-square algorithm, type it out, solve that problem, and move on. Right? You don't get extra credit for coming up with quote unquote extra smart solution. So here's one of my favorite quotes. It is stupid to do things in a smart way when the stupid way works by myself. Right? And also how you can often judge if a problem is brute forceable is by check the scoreboard, and I will touch on that later. Second, you want to ask yourself, is this a graph problem? And the answer to that problem is sometimes really hard to tell because graph is such a versatile and flexible model that it can often be well hidden in the problem description. So it takes experience, maybe even years of it, to identify if a problem fits into a particular graph theory model or no. Well, if you think it's graph theory problem, well, what are your nodes and what are your edges? Trying to identify these two components and ask yourself, well, which of the well-known models, I will touch on that later, fits into the problem description. You also want to ask yourself, is this a geometry problem? Geometry problems are really easily identifiable. Like when you see it, like you're going to know it's geometry. But the unfortunate thing about geometry problem is they tend to be among the hardest problem in a contest. So instead of just digging right in about thinking up a solution, it is often more valuable to ask yourself, is it worthwhile to even spend time to think about how to solve it? More on that later about geometry. String problems are another common type of problems. It's most of the time it's pretty easily identifiable. Like when you read the problem statement, okay, it's like I have a bunch of string, do this or do that, right? When you identify a string problem, the first algorithm that comes to your mind should always be hashing, because hashing tends to give you the best complexity and it just works super well. Does anyone know what hashing is? Okay, whoever don't know hashing, raise your hand. Okay, I'll assume you all know it. So if a problem is hashable, definitely hash your way out because it's most easy to write, it runs really fast, and if you do it properly, it's very less error prone. And if you cannot hash it, try to figure out which of the well-known models apply to your string problem, and I will touch about it later. Dynamic programming is another common type of problem in CP. Like graphs, they can be well hidden, and it takes experience to identify if the problem is dynamic programmable. Right. So when you think a problem is the DP, try to identify what are the subproblems that have similar structure to the master problem. Try to come up with the state space. Try to come up with the state transition functions. And for the most of the times, after you come up with the state space and state transition function, like you're done about constructing an algorithm. Before you type it up, ask yourself, is this fast enough? For most of the times, it will be fast enough because there isn't a lot of flexibility about what states and state transition functions are. So if you come up with one, that's probably the one that the problem authors have in mind. If it's not fast enough, think about, I will talk about this later, but there is a few famous speed up for DPs. So if your DP is not fast enough complexity-wise, try to apply these classic speed ups to pass the time limit. Is the problem really solvable? Really, problem shows up once for a while in competition, especially the lower level ones, and they tend to be the easier ones to solve. So try to, whenever you think a problem is greatly solvable, the first thing to do, well, at least what I personally would do first, is to try to come up with an example when your greedy algorithm might fail, right? When you're into upper level competition, there are many problems that appears to be greatly solvable, but they are not. So definitely check if your greedy algorithm is actually correct. You are not necessarily required to prove it. I will touch on that later. But greedy is always a possibility that you should have in mind. Another easy way to identify if a problem is greatly solvable is by checking the scoreboard. I will touch on that later. And check the data size, because a greatly solvable problem are typically have a linear greedy algorithm. So if the size of your data input is very large, 10 to the 5, 10 to the 6, think about the greedy. Another large family of algorithms is the data structure problem. And the problem statement really goes like, these are the problems that are really easily identifiable. Given updates and queue queries, for each update, do something. For each query, do something, print something. So this type of problem tends to have queue on the order of 10 to the 5. So there are about 100 million queries and also 100 million updates. And so the correct time complexity for each query is something square root of n or log n, or on the rare occasions, log n squared. And another trick to approach data structure problem is to ask yourself, do I have to answer the queries in the order they show up in the input? And if they're not, you're good in luck, because there are some offline query algorithm that allows you to process the query not in order, that allows you to answer each query faster. So you can read in all the queries, rearrange them, answer them in what order that helps you the most, and reshuffle the order in the order they come in and print them. So this is called offline query, and there's a classic algorithm called most algorithm that rearrange the queries in a certain way. It has something to do with the square root bucketing, in a certain way that allows you each query to be answered in amortized time square root of n. If the problem is not offline queryable, think about sectree. Can I sectree my way out? Sometimes you can, sometimes you can't. And when you can't, think about square root bucketing. Because other than sectree, square root bucketing is the most common data structure strategy that you're going to use. The square root bucketing strategy is basically asking yourself, oh, okay, we have a long array. Does it help if I break this long array into square root of n chunks of square root of n? Because oftentimes it will reduce the complexity of each query from O of n to O of root n. Very powerful technique. Finally, there is ad hoc type of problem. Ad hoc is a Latin word which translates rough to specifically for this purpose. And these are the problems which none of the previous models apply. When you see an ad hoc model, it should be pretty straightforward. And this problem tends to have pitfalls in implementation, so be careful about that. So these are 8 types of problems that we often encounter in programming competitions. One quick word about guessing. Contrary to common belief, guessing is a perfectly legit strategy in competitive programming. Now, what do I mean by guessing? So when you see an algorithm, and you feel like, I think the optimum solution has a certain property that allows me to vastly reduce my search space, but I'm just not sure, like I cannot prove it. What do you do now? And my advice for you is go for it. Like assume what your hypothesis is true. So although it would be nice to have a provably correct algorithm, in competitive programming, you don't have to prove the correctness of your algorithm. Well, in a math competition, you do, right? Because math competition is all about proofs. And in CS courses, most of the time, you'll be asked to prove the correctness of your algorithm. But in competitive programming, that's not the case. You'll get the credit for the problem as long as your code produces the correct output for all the test cases. So if you have a conjecture, trying to come up with a counterexample to overthrow your conjecture, if you cannot do that, then maybe your algorithm, maybe your conjecture is just correct. It's just hard to prove. So, general rule of thumb, it is okay to trust your gut instinct. And the more you practice, the more accurate your gut instinct will become. Is anyone in this room taking 182? Comp 182? Okay. So, do you remember in one of the previous homework, there's a problem asking you, okay, you have 2n numbers. You want to you want to pair them up to minimize the max sum, right? You remember that, right? So I was hosting 182 office hour last Friday, and a lot of students approached me and say, okay, Charlie, I do not know how to solve the part B of the problem, which asks us to establish a mathematical result that helps me to develop a linear time algorithm for this solution. And I look at their solution. Most of the students come up with the correct conjecture, which is when you sort the numbers, pair the smallest with the largest, second smallest with the second largest. Most of the students come up this conjecture. Although they are not able to prove it, their conjecture is correct. So, for a CS class, right, you have to prove that in order to get credit. In competitive programming, no, right? So that can literally be a legit problem in an entry-level competition. And when you see this problem, you come up with a conjecture, you code it up, it passes, you get credit. You absolutely don't have to prove the correctness of your conjecture. So that is a big difference between programming competitions and the CS courses. In CS courses or math courses, everything has to be rigorous. But in competitive programming, it is sometimes just just take the leap of faith. It's worth it. So, as my last word in how do you get better at problem solving? Be creative, think outside the box, and it takes study and practice, years of it. Does anyone know where this screenshot come from? Yes, Doctor Strange. It's actually one of my favorite Marvel movies, and it's my favorite quote from the film. Study and practice, yeah, years of it. That's how I get where I am today. And if you want to become a better problem solver, that is what you're going to go through. I will talk more about how do you practice more efficiently in later section. Now let's talk about the book. What do you mean by the book? So pre-COVID ICPC competition allows you to bring a printed 25-page reference document to the competition. And the forthcoming SCUSA is going to allow you to have whatever you have locally on your machine as a reference. Make the most out of these allowed resources. And download the entire internet is probably not a good idea. So the question is, what should you have on your local machine? Well, the answer is the book, but what is the book? So in CP community, the book refers to a collection of pre-written code that serves as standard library that is copy-pastable in a contest setting, or well, if you are asked to bring paper form, then you can basically like copy whatever onto your paper and type it out on your machine. So consider it a library for CP. So the thing is, when you solve a lot of problems, you'll see similar subroutines pop up over and over and over and over and over again. But if you see such a piece of code, it is very helpful to extract that piece of code out and put it inside your book. So if you ask me to code up FFT, which is shorthand for fast Fourier transform, in a competition setting, I wouldn't be able to do that. Like, hell no. I don't have to. Like, I have it in my library. Whenever I need to use FFT, I can just simply copy and paste into my console, and I'll be done to do whatever I need to do next. So book is something you definitely should consider bring to a competition. And what algorithm, routines, subroutines, whatever, should you have inside your book? Here is Charlie's personal comprehensive list about what you should have in your book. So let's begin with graph theory. By the way, what I have here is not necessarily everything that should go into your book, but algorithm you should know. You're either able to blindfold it out, like BFS or DFS. Like, I do not recommend to have it in your library because these two are just so short that you should be able to write it out on your own without thinking. BFS, DFS, blindfoldable, probably not put in your book. Cross-codes, anyone have idea what cross-code computes? Yes, minimum spanning tree or maximum spanning tree. Cross-codes algorithm, classic MST model, you should be able to blindfold it because it's really short and simple. Dijkstra computes the shortest path on a weighted graph. Topological sort, which when you ever have a DAG, which is shorthand for directed acyclic graph, topological sort sorts the node in a linear fashion such that it preserves the orientation of the directed edges, aka all the edges are either pointing forward or backwards, like forward is our convention. Strongly connected components in a directed graph. If node I is reachable from node J and node J is reachable from node I, they're said to be inside the same strongly connected components. And strongly connected components algorithm group these nodes together such that within each component, every two nodes are strongly connected to each other. Max flow algorithm, which given a flow graph, each edge has a capacity. I have source node, I have terminal node. The max flow algorithm computes what's the maximum amount of quote-unquote flow you can send from S to T. And the algorithm highlighted in green means they're sort of like quote-unquote basic algorithm that you should definitely have in your book. The orange one, which I consider to be intermediate level, and the red one, what I consider to be advanced level algorithms. So if you have a limited amount of time to compose your book, do the green first. If you have time, consider orange one. If you have more time than that, consider the red ones. Mean cost max flow, which not only computes the max flow, but computes what's the max flow that has the minimum cost. Konig's theorem is not really an algorithm, but a theorem about bipartite graph. It states that in a bipartite graph, the size of maximum vertex cover equals the size minimum vertex cover equals max matching, and minimum edge cover equals the size of maximum independent set. There's actually it's actually a special case of a much general idea called the linear programming duality. I don't think our CS department is doing this theorem justice. I don't think we even talk about in 182 or 382. If you want to learn more about it, consider of our chem courses, for example, 470 and 471. If you're interested in like this kind of stuff. To SAT is SAT is not like the test you have to take to get into college. The full name is a Boolean satisfiable problem. So given a bunch of Boolean clauses, does there exist a way to assign the Boolean variable to true or false, such that the entire clause is true? Very powerful modeling tool. Probably have it in your book. The reason it's in the graph section is because the algorithm you use to solve to SAT is somehow related to the strongly connected components of a special type of diagram, as you can see here in the slides. Biconnected components in a graph is I, and I is reachable from J from two different paths. Then I and J are said to be biconnected. So biconnected components group the nodes into like components such that within each component, two nodes are biconnected. Central decomposition is a decomposition of a tree that allows you to do certain things in amortized log time. And heavy life decomposition is really a data structure that breaks a tree, as you can show here in the upper right corner, into chains, such that you can query certain things on a tree in log n square time. Next, we move on to data structure. Flowing tree compute the prefix sum of an array in log n time extreme partial data structure. RMQ given an array, query what's the minimum or maximum element from AI to AJ. Very useful. Square root bucketing, which is really an idea. If you break a long array into root n chunks of root n, does it help to solve certain problems? Most algorithm offline query, whose idea is based on square root bucketing. Segmentary, it maintains, well, an array and queries the range, min, max, sum, product, GCD, whatever, from index I to index J in log n time. Union find, which is sometimes called disjoint set. So you have a bunch of elements labeled from 1 to n, for example, and it supports query, two types of query. Union ij, you put I and j in one equivalent class, and find if I and j are in the same connected, if I and j are in the same equivalent class. Trip, this is not actually very commonly used. It is what I call a pseudo self-balancing binary search tree because its self-balancing is based on some probability statement. So when you want to have a binary tree that you want to do certain things that set and maps cannot do, consider trip. Or you can just simply use what we call peanut butter data structure. Okay, policy-based data structure. That's something in the C++ library that allows you to not only implement the set, but you can also query, okay, what's the kth largest element from the set? And like you can do order statistics with PBDS. Split.
You mentioned like there's a policy with a data structure.
Yes.
Like in the library, is it allowed to be seen? Like it's included as part of the first line you mentioned. It's C++. Is that right?
Yeah. It's in the library.
Okay. So it's
Yeah. Okay. It's like if you just if you just include std C++, bits std C++, it does not include PBDS. You need to import like another thing to use this too. But for 99% of competition, like you can import that like without concern. Split and LCT, those are folklore data structures that are good for certain purposes. You rarely need them, but once for a while, a problem will pop up. And those things you should just keep in mind. Like spend some time, understand what they do, and use it whenever you feel necessary. String. The most important string algorithm, which I consider to be tried, is if you have a bunch of words, like in a dictionary, you can throw all these words like into a tree-like structure, as you can see there. It will allow you to answer a query like, okay, if string S is in our dictionary or not. Instead of comparing your string S with every string in your dictionary, just do a traverse of the trie. And if you end on a terminal node of the trie and it matches, then you find your match. Otherwise, your string is not in the dictionary. Rolling hash, as I previously mentioned, the idea is basically turning a string into an integer. So when you want to compare to a string, instead of doing a character by character comparison, you can just compare like the two numbers, or the two numbers are the same, which is much faster than do a character-wise comparison. It's a probabilistic algorithm. It has a certain probability of fail, but that probability can be made arbitrarily small by choosing a proper hash function, which I will talk about later. Suffix array, which given a string, compute all its suffix and sort the suffix. It's a useful, what I call a data structure for certain type of problems. KMP, sometimes called the Z function, is, how do I say it? It provides a linear pattern matching algorithm. If you have a super long string called the text and a relative short string called the pattern, you want to find, okay, if my super long string S contains a substring of my pattern, if you do a character-wise comparison, your worst time complexity is going to be O and N, where N is the length of the long string, M is the length of the short string. Well, if N is like 10 to the 5 and M is 10 to the 3, if you do something like that, you'll probably get TLE. But KMP allows you to do that in O n plus N. It's some sort of magic. You just read about it, and it's pretty challenging to understand, but it's definitely worth it. Ahocratic automaton. Oh my god. Sometimes called the AC automaton. You have a try. You have your Z function. You got your AC automaton. It's that simple. No, I'm lying. Ahocratic, it's very hard to understand, but the idea is to merge your Z function with a try, but it will probably take you several hours to understand. But once for a while, you see a problem that requires you to do a multi-pattern string matching. Whenever those kind of problems pop up, AC automaton is just boom, just a one shot. Math, I say it's more like algebra because you're not actually going to do a lot of like calculus. And geometry comes in next section, so I will say this is more like algebra. Extended Euclidean algorithm, which allows you to solve Bezos identity. Spend some time to look at that up. Modular inverse, and most important, I would say, understand what a finite field is, and understand, okay, if I'm working in a number system that sees Z mod P, then how do I find the inverse of a particular number? fast explanation whenever you want to raise a number or matrix to a very high power, like p to the millionth power. How instead of just doing a million multiplication, I can actually only do log a million, log base 2 of a million multiplication, and it's also called repeated squaring. And by the name, you can probably get a sense of how that automatically happens. Prime sieve. It allows you to compute the identify prime numbers under n, where n is the maximum number you want to consider. How do you factor an integer? All these first 5 routines are extremely useful, powerful tool in competitive programming. Chinese remainder theorem. It is both a theorem and an algorithm. It allows you to solve a system of a linear system of modular equations fast. Gauss elimination, if you're taking a linear algebra class, you should probably know what that is. Linear algebra in Z mod 2. This is more of a concept than an algorithm. Because, linear algebra does not just work with real numbers or complex numbers. You can actually extend all your results from linear algebra to any field of scalars. So when your field is Z mod 2, all your theorem you learn from linear algebra still holds. So sometimes there are questions that ask you about like X or a bunch of bit vectors to get something else. And that is classic linear algebra problem, except the linear algebra isn't done in R, it is done in Z2. So spend some time to try to understand that. FFT, aka fast Fourier transform, treat it like black box. What it does, it multiplies two polynomials in a log period. That's all what it does. Do not consider it to be something scary. You have polynomial A, polynomial B. You FFT them, you got polynomial A times B, period.
So for this one, for the last one you mentioned, do you have a library that you can just compute it?
Yes,
or,
yes.
I mean, in C++.
Not in C++. Like, find the code from like online sources and put it inside your library. It's not a standard C++ routine, but it can be extremely powerful when a certain type of problem pops up. Geometry, several basic routines. Convex hull, given a bunch of points in the 2D plane, find out what are the points that lies on the convex hull. The formal mathematical definition of convex hull is rather lengthy, but like you can get an idea. It's like if you wrap a rubber band like around a bunch of points, like the points that the rubber band touches is the convex hull of that set of points. Judging if a point is inside a polygon, easier said than done. Polygon area computation, there's something called the shoelace formula. You should probably either have it in your mind or have it in your book. The more here comes the more advanced geometry routine, convex polygon intersection and union. If I have two convex polygons, what is their intersection? As shown here. What is their union? As shown here. Minkowski sum, which if you take all pairs of points inside two polygons and you add them, the set you get is what I call the Minkowski sum of the two polygons. Half plane intersection, if you have a bunch of inequality like ax plus b is less or equal to c, then like that equality like represents like a half plane. When you intersect a bunch of them, you get a convex polygon. What is that convex polygon? That's exactly what half plane intersection computes. There is a lot of dark magic in the world of computational geometry, and I simply cannot enumerate all of them, but here are some of them I know that you might want to have in your book. Finally, we move to dynamic programming. As I said before, dynamic programming is mostly about coming up with the right state representation and the right state transition formula. If you have those two, you are most likely done. However, if the time complexity of your DP is not good enough, for example, you have n equals 10 to the 5, and you have 1D, 1D DP. What does it mean? your space you have O of n states, and for each state, the transition cost is O of n, right? So the total time complexity is O of n squared, which will not pass time limit if n is 10 to the 5. There are certain magic you can do to make your DP faster. The first one of these is called divide and conquer optimization. It exploits certain monotonicity in your DP value and to, in some flavor, binary search for where the optimal solution might lie. The other trick is called a convex Hall trick. This is I think more famous than the first one. So sometimes in your DP, you're given a bunch of lines. For example, of form ax plus b, right? You get a bunch of lines, and you want to answer query. Okay, given x and a bunch of line ax plus b, what is the line that maximizes my ax plus b value, and what is the line that minimizes ax plus b value? If you iterate through all the lines, suppose there are n lines, you're going to do O of n work. However, there are smart way to group those lines together that allows you an O of log n query, which is very powerful in certain type of dynamic programming problems. As you can see, both of these topics are red listed, which means they are rather advanced, are not very commonly seen. But if you want to like move into upper division, you should learn this too. And here comes the more metaphysical discussion: is when is it okay to treat things like black box and when it's not, right? So when you have a piece of code in your book and you're solving a problem, sometimes it's very tempting to just use that code as a black box. For example, a max flow code, right? If I have a problem that's about bipartite matching, right? That's a classic application of max flow problem. It's very tempting to just treat the max flow algorithm as a black box and let it do things for you. That is completely okay, and that is actually what you should do. But there are occasions where you need to actually understand how the algorithm works, which means you should not always treat things like a black box, right? For example, if you're in a competition, you're never ever going to write a sorting algorithm on your own because STD sort does that job for you. However, if you know about merge sort, you know a concept that merge sort usually is called what is that? Yes, divide and conquer. I believe if you're in 182, you probably heard about that word. Divide and conquer is a very powerful problem-solving strategy in CP. And the idea of unifying, the reason why unifying is so fast is it utilized a strategy of merging the smaller sets into the larger sets. And it can often turn O of n into an O of log n. So that really gives you some advantage in your running time. So my recommendation is whenever you learn our algorithm, like whenever you are going to put some code in your book, definitely learn how that algorithm works. It is recommended that you type it up on your own. However, if you choose not to do that, spend some time understand how that code works, because there are some times where you need to extract certain information from your code. For example, MST, right? When you're asked to compute an MST, most like standard MST routine will return you the weight of the MST. But what if the problem asks for the edges in that MST, right? So in that case, you should understand how to extract like information from the algorithm, like what are the edges that are in MST. And there are other occasions where you'll be asked to modify a certain algorithm. For example, segment tree, that's a classic example. Right? So in your code, you have segment tree. It most likely only supports one kind of operation, either max, min, or sum, maybe two of them. But in a contest, the range of operations possible, like operators they ask you to implement is vast, right? Even they will ask you range sum, right? But what if there is range max, range min, range XOR, range GCD, range some operations that are just invented by the problem author? Like people do that kinds of things. If you don't know how secretary works, you probably wouldn't be able to modify your secretary code to does the thing for you. Just like do not try to fix your car when you don't know how a car works, right? That's just extremely dangerous. Same is the thing in competitive programming. Do not try to modify your code when you don't know how a piece of code works. So when you try to modify it, definitely understand how a piece of code works. And you should not spend that time in the competition, figure out how something works, do that outside competition. So when you're inside the competition and you need to do some modification, you can just get your hands into it. So general rule of thumb, when you first learn algorithm, definitely understand the idea behind it. Divide and conquer for merge sort, for example. It's recommended that you type the code out on your own because it just feels good when you own the piece of code that you're using. But if you want to decide to take it from internet, I take my FFT out of internet, just for reference. Before adding it to your book, understand how it works. Because there are occasions where that understanding is going to be crucial to your programming, to your problem-solving process. And if you're going to participate in the SchoolSat and you're watching the recording, here is some tip for you. I know that something like 50 slides I just showed you previously about what algorithm you should learn is really intimidating. So my tip for you is you should divvy up the algorithm. You have teammates, right? You have 3 people. So try to divide up the work. You have teammates, so rely on them. I do not know some of the algorithm I mentioned, but for some of them, my teammates knows it. So it's okay for me not to know everything. So it's also helpful to let each person to specialize on a certain type of problem. For example, member A maybe can focus on graphs and data structure, while member B can focus on string and DP. Well, this is for team competition, right? If your long-term goal is to become an excellent competitive programmer, then eventually you're going to learn everything yourself. But this is just a tips for team competition because we all know that ICPC is a team competition. I want to talk about KACTL. It is a great reference. So KACTL stands for KTH Algorithm Competition Template Library. It's basically the book of ICPC teams from Sweden Royal Institute of Technology, shorthanded KTH, and they are one of the strongest ICPC team on this entire planet. So the long story short, they are someone you can trust. Their book is open to public. It contains pretty much everything you are going to need. Their code is very compact, aka short, easy to type up, and the correctness and the performance of their code is well tested. And their code is widely trusted by civic community. So whenever you want to code for a specific algorithm purposes, instead of searching like a drunken goose on the internet, KACTL should be your go-to place. Now I want to talk about some in-contest strategy. What to do? Okay, you finally type up your solution and you submit your solution. Of course, you want to get AC, which is that green mark we all long for, accepted, right? But when you don't get AC, here are something else that you might get. WA stands for wrong answer, TLE, time limit exceeded, RTE, runtime error, and MRE, memory limit exceeded. I would say that WA is probably the most common type of your code didn't pass judgment. And when you see LA, when you see WA, first thing first, do not panic. I know there are a lot of newbies who spend 40 minutes type out their code, submit to judges, ECWA, and they get like, how can my code be wrong? Like, right? If you're wondering like why I know it, I was that person like a couple years ago. Okay. I know like you are trained to think critically and judge authorities, but in programming competition, when they say you get it wrong, you get it wrong. Okay, accepted it. And start thinking what might possibly gone wrong. So this WA judgment is deserving of an entire section, so I'll save it for later. I will talk about TLE. So when you get a TLE, the first thing you should be thinking is what is the time complexity of your algorithm. You plug the largest set of your data, your tested data, and you throw it in the old formula of your time complexity and see if it's on the order of 10 to the 8. If your input is in the order of 10 to the 5th, the input can actually take quite a long time, like half a second. So when you're dealing with a problem with input size of 10 to the 5th, and you get TLE, use the black magic, okay? So that's the 2 lines of black magic that automatically give you a 5 times speed up on your input. Use that. If our output of your program is on the order of 10 to the 5th, the time it takes to print the solution can also take up to half a second. So if that is the case, use printf instead of cout, because printf is much faster than cout. So learn how to use printf. Learn how to use the placeholders like %f, %n, %s. Memory limit exceeded is also type of solution, type of judgment you might get. It personally, I would say it rarely happens. Does anyone of you know why that may be the case? Why memory limit exceeded rarely happens?
So the amount of memory you get is like the CP is generally pretty huge.
Yes, that's the first reason. They are very generous in memory they are going to allow you. The second reason is you're probably going to get TLE before MLE, because when you allocate a very large chunk of memory that will cause MLE, it takes time to do that, right? So probably before you reach the memory limit, you're going to reach your time limit first. So that's why TLE is much more common than MLE. That's just my personal view on this issue. And when you run into RTE, which stands for runtime error, first thing to check, does your code generate the correct answer and exit without error for all the sample test cases. And when you run into runtime error, it's most likely because you visit an array vector out of bound. In Java, that's probably not going to be the case, because when you try to visit something out of bound, the compiler will warn you and you would know, right? Same is the issue in Python. But C++ is kind of annoying on this issue, because you can run a piece of code locally without any problem, and when you upload your code to the judges and they run into a runtime error. It's because C++, it doesn't warn you when you exit a memory that is out of bound. When you use an index that is really out of bound, something is going to go wrong and causing your code to crash. If your sample test case is really small, you're not going to do something that's really outrageous. So it might just cheese by without you catching it. But when you use a larger set of data, that problem will arise and it will blow your code up. So think about the possibility of did you visit an array or whatever data structure out of the bound. Did you divide it by 0? That is another common mistake, that whenever something is 0, that sometimes that deserves special treatment. So consider that. Did you initialize all the variable use? Unlike Java and Python, when you create a variable, like their values are automatically assigned to default value, like to 0, for example. In C++, when you create a variable, it just sits in the memory, and whatever is previously there in the memory will be stored in your variables. So whenever you create a variable, initialize it, set it to 0 or something else. And more on it in the common mistakes section. So KACTL has a more comprehensive list of what to do when you get blah. This is on your first page. So if you're interested, check it out in your free time. And I do have a personal list of mistakes that I tend to make, and also later foreshadowing it in the common mistakes section. A word on time management. So how the scoring in ICPC works is teams are ranked first based on the number of the problems solved, and the ties are broken based on the total solved time. So the team who solves the most the problem will be ranked very high. If two teams solve the same number of problems, but team A solved the problem using less time, team A will be ranked higher. So suppose there is an easy problem and a hard problem. The hard problem takes 1 hour to solve, and easy takes you 10 minutes to solve. If you go for the hard problem first, you're going to spend 1 hour solve it, and you're going to spend another 10 minutes to solve the easy problem. Now, what is the total solve time? It's 1 hour, the time it takes to solve the hard problem, and by the time you start the easy problem, 1 hour has already passed, so you're going to spend another 10 minutes on the easy problem. So your total solve time is going to be 2 hours and 10 minutes. But if you go for the easy problem first, you're going to spend 10 minutes to solve it, and another hour to solve the hard problem. So your total solve time is going to be 10 minutes plus 1 hour and 10 minutes, which is 1 hour 20 minutes, much less than 2 hours and 10 minutes. So the conclusion is, go for easy problem first. Yes?
You explain the time thing again about doing the hard one first, 2 hour time.
Okay. So the solve time of a particular problem is defined by the time of beginning of the competition and the first time a correct solution is submitted. Does that make sense? Yeah, so that's why we have the numbers we have here. Check the scoreboard frequently. I have foreshadowed these slides in the previous slides multiple times. If you think a problem is hard, but you check the scoreboard and you see a bunch of teams solve the problem really fast, then you probably misjudge the difficulty of the problem. So something you can do when that is the case. First thing, you can ask your teammate what they think about the problem, because when you are the only person who is reading the problem, you think it's hard, it might not, like the other people might not share the same view, and they might be able to like clear the clouds and see the things better, because it is much harder for two people to misjudge the difficulty of a problem than one person. Ask your teammate. Second, did you understand the problem correctly? Jesus, I cannot I cannot state this with enough emphasis. Read the problem word by word. Understand exactly what the problem is asking. Because when you misunderstand the problem, you might be tempted to solve a much harder version of the problem. The problem isn't even asking. You cannot believe like how many teams screw up on this one. I will talk about that in later slides. If you misjudge the difficulty of the problem, consider how it can solve. Maybe it can brute force. Like maybe a brute force algorithm will just pass. Like maybe the constant of a brute force algorithm is just too low. That even a algorithm with a worse complexity, with a bad complexity, will cheese through if you can implement it in a very efficient fashion. Maybe it's greedy. I mean, it's possible that some greedy structure exists that you can exploit. And my final words on this type of problem is just try not to overthink it. When a lot of teams solve it really fast, it's probably something really stupid. Like try to think it in stupid way, and a solution might arise really easy. Finally, geometry problem. Here is the name. So competitive programs are panicking, running away from something, and that thing is a geometry problem. How should I even start talking about this? There are only two types of geometry problems. The ones that are easy, and the ones that are not, and the ones that are just not doable. There is no middle ground. So in upper level competitions, geometry problems, they're monsters, okay? It tends to be the hardest problem in the entire contest. Even the best teams, I mean MIT and Waterloo, they struggle with geometry problems, okay? So if a geometry problem feels hard, it is probably very, very hard. And it is okay to give it up. Like, if it's hard geometry, let it go. Like, you might be better off spending your time on other problems than wasting your time trying to crank out the geometry problem, which is really, really hard to get AC. Another comment on geometry problems are if you have the right book code. That's why I emphasize book code so often. If you have the right book code towards a specific geometry problem model, the problem is usually one-shotable. Just code, like copy paste your book code, do some input and output, boom, you're done. That's when you have the correct book code. If you don't have the correct book code, then it is nearly impossible to code up a robust, correct geometry routine on the fly during a competition. So have a lot of geometry templates, and if you don't, and if the problem is hard, think about giving up. It's okay. Next, I will talk about common mistakes that beginners and even intermediate competitive programmer tends to make. Read the problem. Read the freaking problem. Understand, okay, sometimes it might be a case that you read halfway through the problem, you're like, oh, I know exactly what this problem is asking, and you start typing. Stop, read the freaking problem, word by word, every single sentence. Because I would say ICPC, okay, here is a bit of like a culture thing. The problem on code courses tends to be pretty straightforward. I think if you're doing CL, you probably can tell that it's like given this, alter this, given this, compute this. But the way ICPC problem works is they will begin by telling you a story, and they will hide the problem in the story, and you want to like figure out. So like sometimes it might feel a bit of wasted time reading the story, but it's worth it because there might be a sentence in the story that allows you to assume something really specific about your input data. And that is often what makes the difference between an NP hard problem and a problem that is linear time solvable. For example, there a couple weeks ago I was doing a problem, like when I first read a problem, it just reads like solve a set packing problem. I was like, but that's NP hard, and the n is something like 1,000. No, that's not even 1,000. I think that's something 10 to the 5. But then I read the problem again. There is a line that's saying, like, all sets, like, a set is either like subset to non-set, or it is a subset of another set. There's a terminology for that the collection of sets is laminar. When a collection of sets is laminar, solving set packing problem is linear. You can basically construct a DAG out of those sets, and you do a DP on those stack. So read the problem, make sure you get everything that you can assume of our problem, and make sure you get everything you cannot assume of a problem. Because sometimes when you code up a graph routine, it is very natural to assume the graph is simple. What I mean by simple, there are no parallel edges, there is no self loops. That is true for most of the problem. But once for a while, if like the problem author are just evil. They might throw you a problem where this assumption fails. So read about what you cannot assume about input data. Are parallel edges allowed? Are self-loops allowed? That's for a graph. If you have a string problem, is it possible that I have repeated words in a dictionary? These are something that might be very easily overlooked when you're coding the algorithm. And the algorithm you code out, which are based off these assumptions, might just not work when these assumptions are broken. So read the problem. There is just nothing more frustrating than spending 40 minutes to code up something that the problem isn't even asking. So read the freaking problem, please. Floating point arithmetic. That's another common pitfall in programming competitions. Floating points arithmetic aren't exact. You probably have already know that. So if you can avoid them, by all means avoid them. So for example, if I'm to compare two fraction, for example, is a over b less than c over d. Here are two different ways to do it. First, you can convert them into double and just do a division and compare the value of the quotient. Or another way to do it is you first convert them to long, and you do the cross multiplication, and you compare like the result. Which one do you think is better?
Second.
Yes, and why?
I don't know. Seems.
Well, your intuition is definitely correct. Because division is not exact. Like floating point division is not exact. If the real value of a over b and c over d are very far apart, the first approach will most likely work. But if you're really, really close, then things might go wrong. So whenever you can avoid floating point arithmetic, avoid them. And in upper level competitions, the judges will specifically design a testing case that is intended to make the first approach against WA. Like they are going to do that. Like they are going to give a very carefully engineered input data that is intended to make the first piece of code fail. So have that in mind. Another thing about printing floating point number is make sure you print the right amount of digits, right? So couts, it's very easy to use the first output method when you don't have much experience. That is a very bad practice because cout might not give you enough correct digits, and when it don't, you will most likely get WA. The correct way is, one of the correct way is to use printf. You specifically ask the printf to print 9 digits after decimal place. As a general rule of thumb, when a problem asks you for incorrect digits, you should print out n plus 1 digits, if not more. When you don't pay attention to floating point arithmetic detail, this is what happens, okay? It sucks, so avoid that, impossible. One quick note about hashing, which I talked about when talking about string algorithms. So when there are n things to be hashed, all of n things to be hashed, you definitely want to make sure the range of your hash function is O of n squared. And just to make it extra safe, make it 10 times n squared, and that will probably be a safe range for your hash function. Does anyone get this reference? Anyone guess? What might this refer to? No idea? Who have taken a statistics course at us? Did you guys talk about birthday paradox in your class?
Yes.
Yes, so in a room with more than one, yes? Yeah, if in a room there are more 23 people, then there is over a 50% chance that you can find a pair of people that share the same birthday. Why is it 23? That is approximately the square root of the number of days in a year. So if you consider people, if you consider person to be key and their birthday to be their hash value, which means if you have over a square root of the number of elements in its range, it will be very likely to see a hash collision, right? So, and there is a cybersecurity term called the birthday attack. It is a type of attack performed by hackers that exploits the so-called birthday attack. So birthday attack, you smash a birthday cake on someone's face. That's the reference. And a tip for upper level competitors: when you decide to write a hash function, avoid using the famous prime. And by famous, I mean 10 to the 9 plus 7, 10 to the 9 plus 9, 998, 244, 353. Those, if you have done enough problem, like either on CF or on whatever sources, you probably have seen those numbers for over and over and over and over again. These numbers, either they're easy to remember, that's the case for the first two prime, or they have some special really nice property for them in the second case. When you're asked to mod this prime, well, definitely use whatever they ask you to serve as a mod base. But when you are writing your own hash function, do not use this prime. Because as I say, sometimes the problem stater are just not nice people, and they will design a set of data to specifically fail those mods when you decide to use them. So try to use a prime that is not famous. And like you can just check like primes greater than 10 to the 9, and there are a bunch of them. Pick your favorite. No, don't pick these two. Some debugging hacks. So here are the most common runtime error that you might run into. Like when you're testing your code on your local machine, like when you submit to your judges, you will just get like RTE. But when you run it on your local machine, you run into error. It's probably one of these two. C a bunch of zeros 374. That's heat corruption. C a bunch of 05, invalid memory access. C a bunch of 0 FD, stack overflow. C a bunch of zeros 94, that's divided by 0. It's very useful to keep those numbers in mind so you know what might possibly go wrong with your code. Another useful debugging technique that I personally find useful, assert false. It will basically turn an WA into an RTE because whenever that line is run, it automatically runtime errors the code. So if you think, okay, so at this place of my code, x should equal to 0. Well, is that actually the case? Well, you can just assert x equal 0. If that does not hold, you automatically RTE your code. So you know, okay, this is working well. It helps you to narrow down the source of your bug. This line is very useful. It's basically debugging output. It prints the variable name and the variable value of a certain variable. And as I promised, here is my personal list of a common source of bugs, and here are two snapshots of like the subcategories. I related, did you print yes when asked to print yes? And I know that's stupid, but you'll probably felt that at least once in your CP career. Is your output format correct? Blah, blah, blah. Do you really know C++? That's language-related error. Vector pushback creates a copy of the input. Are you modifying container while iterating through it? Those are common source of mistake when using C++. So give the document a look and have them in mind when you're typing out your code. I think this is the second to last section in there. We're almost get there to the end. ICPC, as I said before, ICPC is a team competition. So it's a 5-hour competition. You have 3 people, 1 laptop. What does that mean? you have 15 man hours but only 5 computer hours. So computer hour is a scarce resource, so try to make the most out of it. So when there is another teammate having a complete algorithm in his mind and he's trying to type it up, but you're using the computer, like if you're not typing, you're thinking, give the machine time to them. Let them type up their solution, where you can just stand back and think about what might possibly go wrong with your program if you're debugging, or try to think out, okay, what should I type next? When there's, as I said before, when there's a queue for the keyboard and you're debugging, print your solution out and debug it on a piece of paper if there's another person waiting for the keyboard. And when your teammate is using the keyboard, try to use pencil to write down like the core part of your code. Anyone has ever taken AP Computer Science? Okay, some of you. Right. You still remember the day when you write Java program with pencil and paper? Yeah. I think there are only 2 occasions in this world you have to write a program using pencil. The first one is AP Computer Science. The second one is the ICPC competition, where there's only 1 laptop allowed. Here are some do's and don'ts. Do not breathe down the neck on someone who is typing out a solution. Right? When you're just typing, and your teammate is like, how are you gonna feel? Not good, okay? Not good. Like the pressure like they put on you is probably going to make you make some mistakes. So do not breathe down the neck of whoever is typing out the code. You're distracting them, okay? And trust your teammate. I know sometimes you want to develop an urge like are you done? Are you done? Are you done? Do you know what they're doing? Stop. Trust your teammate. They know what they're doing. Right? It's about trust. So trust them. When you're stuck with your implementation and there's another teammate waiting for the keyboard, step back, let them have the keyboard while you think about like what might be the next step in your implementation. And like, when you take a step back from your screen and you like, re-look into a program like from a more or less fresh point of view, it might be like easier trying to find where the bug is. And lastly, just like problem solving, teamwork is something that takes practice to perfect. So if you're going into a team competition, the forthcoming schools are, for example, and you want to do a practice, try to practice with your teammate to familiarize how to teamwork with your team. And I want to show you guys something that is called team think tank strategy for team competition. So the general guideline, the philosophy behind this strategy is a good problem solver is not necessarily a good programmer, and a good programmer is not necessarily a good problem solver. Like there are people out there who are both, but whenever like you have a person on your team who is very good at problem solving and the other person is very good at programmer, this is a really valuable strategy for your team. So 2 team members form a think tank. Usually it has like one of the best problem solvers on your team to be in the think tank to analyze the problem and propose a solution, and the third person who is really good at implementation code out the solution and submit. So the think tank will look through the problem, find the most approachable problems first. Remember, solve the easy problem first. Find the most approachable problem, communicate the idea to the third person, and the third person type it up, while the think tank keep browsing through the problem sets and find the next easiest solution, communicate it to the third person, and repeat process. A benefit of having 2 pair of eyes on a problem set is it's much harder for 2 people to misjudge the difficulty of a problem than 1 pair of eyes, say. And here is a great reference for how to teamwork properly in ICPC-like competition. It's titled Teamwork in Programming Contest 3.1 equals 4. It's, if you click on that link, it's one of the first documents with this title. If you have some time, look that up. For the next section, I want to talk about more long-term improvement, metaphysical, philosophical topics of this lecture. So practice both smarter and harder. So the first thing I want to bring up is how to find the problems to practice. So I think the first thing you want to consider is you want to find a problem that you can find the tutorials on. Because not knowing how to do a problem during your practice is okay, but after the practice, if you still cannot do the problem, it's a problem, right? Pun intended. So some good problem sources that you're pretty much guaranteed to be able to find sources. KACTL, if you participate in the NAQ, you probably know it's a problem bank where a lot of the ICPC competitions are held. So there are some really good sets on KACTL. For example, Newark, S-Work. It's Northwest European Regional Contest and Southwest European Regional Contest, I believe. These are two really good sources because you're guaranteed to find problem like official editorial on their official web page. And past ICPC, NAQ, and regionals, these are also problem sets that you can most likely find tutorials on the internet. Croatian Open Competition in Informatics, also a classic problem bank. You can find the solution on their official website. Past Google Code Jam, Kickstart, excellent source. HackerRank and Codeforces, they have, I think, editorials for not every single problem, most problems on their website. So good sources. And here is another quote. There is no shame looking up the solution when you're stuck. You learn more from the problems you can solve than the ones you can by myself. When you are doing a practice and you get stuck on a problem, it's most likely because one of the three reasons. The first is you didn't see the solution. It's okay. It happens all the time. When you practice more, like your vision will become more and more clear, right? So you're going to improve your ability to see the solution. If that is the case, when you read the editorial, you'll be able to understand, and there will be aha moment. So this is the structure that I didn't see. So this is the model that I should apply, right? There should be this aha moment when you're reading editorial, and after you understand the editorial, go back and review the problem. The second case when you get stuck on the problem is there's a theorem or concept you didn't know, right? Because if you haven't seen a principle of inclusion and exclusion, you might run into a coding problem that use this theorem that you aren't able to solve otherwise. And when you read that tutorial, like PIE, what is PIE? It stands for the principle of inclusion exclusion. When that is the case, read about the theorem, definitely try to understand the proof of it. So whenever you understand the proof of something, like mentally it strengthens your understanding of the theorem, and of course go back and cure the problem. The third reason when you can get stuck on a problem is there's an algorithm, model, you can call that, or a data structure that you simply haven't seen before. For example, if you haven't seen, for example, min cost, max flow, or secretary before, when you run into this type of problem, you just, what should I do? Right? You don't even know the model. If that is the case, look up the algorithm, try to code out the thing on your own if possible. Otherwise, as I suggested before, if you decide to copy it from internet, understand the code. And go back and kill the problem, and lastly, add it to your book. So when next time you see the problem with a similar structure, you can just basically copy that code, paste it into your console, and boom, problem solved. And my next point is practice on problems in your learning zone. Oh, what do I mean by that? So, like, this is a bit of psychology about learning, right? So, there are sort of three kinds of zone of certain level of difficulty of problem can lie in. If it's in your comfort zone, it's like, nah, this is easy. I can solve it in 5 minutes, right? If it's in your learning zone, like after a bit of struggle, you might be able to solve it, or after a bit of struggle, you might not be able to solve it. But it's still like approachable that you can understand what you're doing. And the third type of like zone is the panic zone. You have absolutely no idea what this problem is about. It's just too hard, right? So definitely practice in your learning zone. And one tip I want to bring about to how to identify your learning zone is by looking at the problem difficulty. Like for example, code forces, the classic ear rating of the problem. That's what the code forces use. If you're practicing on code forces, try to practice with the problem of your current rating plus about 200. That's about from a personal experience where your learning zone is going to be. If you're practicing with KACTL, practice with problem of your comfortable difficulty, whatever that means. Well, I should probably explain what that means. It means like the problems that you can comfortably solve. Like the hardest problem you can comfortably solve, the difficulty of that problem plus 1. That should be about where your learning zone is going to be. Finally, some good resources about where you can learn algorithm and data structures. cpalgorithms.com is an excellent tutorial website. You can find both the explanation and implementation of classic algorithm and data structure in programming competition. The second source is USCO.guide. USCO is a USA Computing Olympiad, so it's the informatics Olympiad in USA. I did that when I was in high school. I did okay, by the way. And it contains a very complete set of common algorithm and data structure appears in a programming competition. It's not as personally, I think the explanation in USCO is not as good as the CP algorithm, but I personally think USCO provides a more comprehensive list of things you should learn. So be sure to use those two resources, like complement each other. With that said, that's the end of my presentation. If you have questions, comments, complaints, bring it up.
Yeah, very personal question, but I hope this will make like others feel frustrated. But I want to ask, like, what's your comfort zone on the like the code forces? Like, what's the range of scores that you feel comfortable solving?
I'd say personally at probably 2,300. My comfort zone or my learning zone?
Both.
I think my comfort zone is about 2,000, and my learning zone is about 2,300 or 2,200. I'd say the lower one. Any other question? Yes.
I guess earlier resources for like, did you learn this through going down the UCL website, or did you like have a textbook or anything else?
Oh, sorry, I did not hear that clearly.
Like, is there like source like textbook or something else, like a more comprehensive source that like covers a lot of the?
Do you recommend textbook?
Yeah.
Textbook? Robert Sedgwick's algorithm, first edition, is where I learned a lot of the graph theory stuff. It's the textbook used as Princeton's introduction to algorithm courses. I personally think our Comp 182 covers a lot of the graph stuff. For example, I think the 182 people, you learned about MST, you learned about Dextra. In 382, you will learn about flows and dynamic programming. So I think the course at RISE covers a lot of these materials, but if you want to be really good at CP, yeah, go to the CP algorithm and the user guide. And there is the CRLS, I believe. It's the classic algorithm that's about like this thick. That I do not recommend read like every chapter of it. Read some chapters from it that you find useful. Yeah, that's my comment on that. Any other questions? No?
Alright, so I think we already went like over about half an hour. I really appreciate like everyone stay here, and I think like Charlie really done a great job like explaining a lot of the methodologies, like high meta stuff. I mean, yeah, I met a lot of good programmers, but like very few of them I know of like personally. They're really good at explaining stuff, and like especially their own methodologies, which I think Charlie really did a good job. And we'll be like uploading all of this stuff, the videos and the slides to the like, and I'll share with you the link. So I just want to thank everyone here for attending and Charlie for his own time.
Thank you.
Honestly, it's an exciting moment. We got the pizza, and yeah, unfortunately the pizza guy was lost, so we don't have pizza anymore. So you have 20 minutes to get the server ready. I'm just kidding. Okay. Okay, so we got actually a lot of pizza. So each one of you can probably get one pack.
Okay.
Not like.
We were too optimistic about the.
Also have a good time like today for the dinner.
Yeah, you